Welcome to today's deep dive. We're jumping straight into a stack of sources that has basically set the entire astrophysics community on fire over the last few weeks.
Oh, completely on fire. It's been a wild ride.
Right. I mean, we're looking at a series of recent preprints analyzing the absolute latest data from NASA's James Webb Space Telescope.
Along with some incredibly intense debate pieces playing out in major cosmology journals right now.
Exactly. And our mission for this deep dive, for those of you listening, is to unpack an anomaly that, according to everything we know about the universe, simply shouldn't exist.
It really shouldn't.
We are talking about the discovery of a colossal structure, like a massive wall of galaxies just sitting out there at the absolute edge of the observable universe.
Yeah, and as a science journalist, my job is generally to temper the hype, to keep things grounded.
Which is why I love having you here.
I try. But honestly, when I read cosmology papers proposing paradigm-shifting anomalies or throwing around terms like multiverse collisions, my immediate instinct is just deep skepticism.
Oh, sure. Totally natural.
Right, because we have seen instrumental glitches or calibration errors masquerade as cosmic revolutions before.
Definitely.
But going through the empirical data in this stack of sources, I mean, the gravitational footprint of what JWST has captured is incredibly difficult to dismiss.
It really is.
It presents a structural anomaly that fundamentally challenges the established timeline of our universe.
Okay, let's unpack this. Because I am reading these exact same papers, and as an astrophysicist, my mind is just racing.
I can imagine.
We are looking at a structure spanning billions of light years, just sitting out there in the ancient cosmos, blatantly defying our models of how and when matter is supposed to clump together.
It's massive.
It is, and it forces us to ask a terrifying question.
Yeah.
What happens if the universe we live in isn't an infinite uniform expanse, but actually has a boundary?
Right. And to understand why this specific structure is causing such an uproar, we really have to establish the baseline of how the universe is supposed to be organized.
The status quo, basically.
Exactly. The sources focus heavily on the standard model of cosmology, which is often referred to as lambda CDM.
Right, the gold standard.
Yeah. And this model dictates that if you zoom out far enough, the grand framework of the universe, the galaxies, the dark matter, the vast clouds of gas, it all forms an intricate three-dimensional network known as the cosmic web.
And the defining rule of that cosmic web is uniform distribution over massive scales.
Uniformity is key.
Right. The standard model relies on something called baryon acoustic oscillations, which is a fancy term, but it basically means ripples of density left over from the Big Bang. And these ripples dictate that filaments of galaxies should be scattered relatively evenly across space. Think of it like a fine mist filling a massive room.
That's a really good way to visualize it.
But the JWST data we are analyzing paints a completely different picture.
A radically different picture.
Yeah. Deep in the ancient cosmos, instead of a relatively even mist, astronomers detected a jaw-dropping concentration of matter.
Just a solid wall.
Exactly. A literal wall of dense galaxies being pulled together by a gravitational force so intense it just breaks our current models of structural formation.
And, the time frame is the critical failure point here.
Because of how long light takes to travel.
Right. Because the speed of light is finite, when JWST observes a structure billions of light years away, it is capturing light that left those galaxies billions of years ago.
Like looking into a time machine.
Exactly. We are seeing this region of space as it existed in the very early epochs of the universe, mere hundreds of millions of years after the Big Bang.
When things were vastly different.
Very different. Under the lambda CDM model, the early universe was just a hot, dense plasma. Radiation pressure actively fought against gravitational collapse.
Yeah, and gravity is notoriously weak and slow anyway.
Incredibly slow.
It takes an immense amount of time for dark matter halos to form, to pull in baryonic gas, to ignite the first stars, and to eventually drag those stars into clustered galaxies.
It's a very tedious process.
It really is. So I love to use this thought experiment to explain the timeline problem to everyone listening.
Let's hear it.
Imagine you are on an archaeological dig.
Okay.
You are excavating a sedimentary layer of Earth that definitively dates back to the Stone Age.
Right, so you expect to find, flint tools or maybe a primitive fire pit.
Exactly. But instead, you brush away the dirt and you uncover a fully built, modern glass and steel skyscraper.
Wow. Yeah, that puts it in perspective.
Right, it shouldn't be there.
It's a massive temporal anachronism. A structure of that mass and density simply did not have enough time to form that early in the universe's lifespan.
The math just doesn't add up.
No, it doesn't. The internal mechanics of our universe, specifically the slow, methodical accumulation of mass via gravity, just cannot account for it.
But let me push back a bit. Or rather, let's address the elephant in the room.
The alternative explanations.
Yeah, because I know you look at these papers with a skeptical eye. Could we just be misinterpreting the data?
It's always a possibility we have to rule out.
Right. Some of the debate pieces in our stack suggest alternatives. Like, what if this is just an extreme case of gravitational lensing?
Where foreground mass is warping the light of background galaxies.
Exactly, to make them look like a solid wall when they really aren't. Or maybe our calibration of JWST's photometric redshifts is just, off.
Well, those are the exact questions the scientific community is raising, and they're essential to ask.
We have to cover all our bases.
Right. Gravitational lensing can absolutely create cosmic mirages, magnifying and distorting background objects.
Happens all the time.
It does. However, the subsequent spectroscopic follow-ups detailed in these papers seem to completely rule that out.
Because they looked at the specific light signatures, right?
Yes. The researchers measured the spectra of these galaxies, which confirmed they are physically clustered at the exact same distance. It's not an optical illusion.
That is wild.
And as for redshift calibration errors, to mistake a local structure for something this distant and massive would require a catastrophic failure across multiple independent instruments.
Which is highly unlikely.
Very unlikely.
Which leaves us with the spectroscopic reality of the wall. And that leads to the causality problem.
The big mystery.
Right. If the internal mechanics of our universe couldn't build this skyscraper in the Stone Age, we are forced to look for an external cause.
Something outside our normal physics.
Exactly. The data makes it look as if an impossibly strong localized gravitational pull organized these galaxies into a neat, uniform line.
And this is where the papers in our stack pivot from standard astrophysics to theories that usually get you laughed out of the observatory break room.
Oh, absolutely. The leap to the multiverse hypothesis.
It is a massive conceptual jump.
It really is. But the researchers argue it is a jump forced by the lack of viable alternatives within the standard model.
Right. And the framework they are utilizing for this is eternal inflation.
Which is such a fascinating concept.
It is. The theory posits that the rapid expansion of space following the Big Bang didn't just happen once and then stop.
Like blowing up a balloon and tying it off.
Exactly. Instead, inflation is an ongoing process in a broader cosmic ocean.
And the math behind eternal inflation is incredibly elegant. It relies on a scalar field dropping to its minimum energy state.
Right.
But what if that drop didn't happen everywhere simultaneously? What if inflation stopped in our localized pocket, creating a bubble where things cool down enough for stars and galaxies to form?
While space continued expanding exponentially outside of it.
Yes. Constantly spinning off new, separate universe bubbles. For decades, that was purely theoretical math.
Math on a chalkboard.
Basically, yeah. But now, physicists are arguing this cosmic wall is empirical evidence of it.
And what's fascinating here is the specific mechanism they propose to explain the wall itself.
The bruise.
Yes. The hypothesis suggests this isn't just a dense cluster of galaxies. It is a permanent scar. A multiverse bruise.
Just the imagery of that is incredible.
If another bubble universe drifting through that expanding cosmic ocean collided with our bubble billions of years ago, the energetic impact would leave a profound mark.
So let's break down the mechanics of a bruise like that.
Yeah.
Because a collision between universes wouldn't look like, two cars crashing.
Not at all.
It would be an immense transfer of energy, creating a shock wave in the primordial plasma of our early universe.
A massive ripple.
Right. And that localized shock wave would create a region of hyperdensity. That overdensity would seed dark matter halos exponentially faster than the standard quantum fluctuations we usually rely on in the lambda CDM model.
Which neatly solves the timeline issue.
Exactly. It builds the skyscraper early.
The papers describe this bruise manifesting not just as a wall of galaxies, but as an unnatural alignment within that wall.
Like they're all spinning the same way.
Yeah, they're looking for anomalies like a shared parallel spin axis among the galaxies along this boundary, or a stark temperature dipole in that specific region of the cosmic microwave background.
But you're still skeptical.
I remain highly cautious. I mean, string theory and multiverse models are infamous for lacking testable, falsifiable predictions.
Fair point.
Retrofitting the multiverse hypothesis onto a newly discovered structure feels dangerously close to confirmation bias.
I understand the hesitation, I really do. But I'd argue the structure itself is the testable prediction we've been waiting for.
How so?
Well, physicists have hypothesized for years that if bubble collisions occurred, they would leave localized anisotropic rings or walls in our sky. We just didn't have instruments sensitive enough to see them until JWST. If this structure is the boundary line where the impact occurred, we have to confront the reality of what we are observing.
Which raises an epistemological nightmare, honestly.
Oh, completely.
If we're looking at the boundary line of our bubble, where the impact of another universe occurred, we are standing at the absolute edge of our conceptual map.
Exactly. Our instruments, our math, our entire framework of general relativity are calibrated to measure light and gravity as they function under the physical laws of our universe.
Only our universe.
Right. But if another universe has different fundamental forces, like perhaps a different mass for the electron, or a gravitational constant that operates on an entirely different scale, how do we even begin to measure it?
We can't directly. That's the problem.
Yeah.
If we are seeing the gravitational influence of a foreign universe pulling our galaxies into a wall, we are measuring a shadow.
A footprint.
Exactly. We are observing the secondary effects of physics we cannot truly comprehend because they operate outside the parameters of our reality. It highlights the profound limits of human observation.
So what does this all mean for us, for the people listening right now?
It's a big shift.
Because we have moved from analyzing a structural anomaly to discussing something with catastrophic consequences for modern science.
Catastrophic is the right word.
The physics papers in our stack are bordering on a state of panic.
Yeah.
Because if this bruise is real, it completely shatters Albert Einstein's foundational equations.
And to understand the magnitude of this disruption, we really need to look at the cosmological principle.
The backbone of cosmology.
Yes. Almost everything we know about modern physics, specifically the application of general relativity to the evolution of the universe, is built on the assumption of isotropy.
Which means looking the same everywhere.
Right. Isotropy dictates that on a macro scale, the universe looks exactly the same in every direction.
So if you point a telescope north, south, east, or west, you should see roughly the same density of galaxies.
Exactly.
The cosmological principle is the bedrock of the Friedmann equations, which we use to calculate the expansion rate of spacetime. Those equations only balance out if matter is smoothly distributed.
But this wall introduces a massive, undeniable anisotropy.
It ruins the balance.
Completely. You have a colossal, heavy structure on one side of the cosmic room, throwing off the entire gravitational equilibrium. If the universe is not uniform, then spacetime is not expanding uniformly.
Gravity suddenly has a directional bias.
Yes.
Which means our understanding of the cosmological constant, the dark energy driving the expansion of the universe, might be fundamentally flawed.
It's a scary thought for theorists.
If dark energy has to fight against a massive wall of galaxies on one side of the universe, but stretches freely on the other, our entire model of cosmic expansion just breaks down.
We aren't tweaking a decimal point here.
No, not at all.
The discovery of this wall implies that general relativity might only be a local approximation, valid in our immediate cosmic neighborhood, sure, but completely insufficient for describing the universe as a whole.
That is just mind-blowing.
The source material we are analyzing frames this beautifully, actually. One of the authors uses a metaphor that really stuck with me.
Oh, I think I know the one.
Yeah, they said finding this invisible wall, this massive structure that defies the cosmological principle, is like mapping an ocean for centuries, charting the currents and the depths, only to suddenly bump into an unscalable reef that shouldn't exist according to your hydrodynamic equations.
Wow.
It reminds us how completely small and blind we are to the true scale of the cosmos.
I want you listening to really consider the implications of this.
It's a lot to take in.
Should we view this panic in the physics community as a crisis, or as the most thrilling opportunity for discovery since Einstein first published his theories of relativity?
That's the big question.
Because to me, knowing that our equations are incomplete isn't a failure of science. It means the universe is vastly more complex and infinitely stranger than our current mathematical frameworks can capture.
And that tension is the driving force of all scientific progress. A crisis in the old model is the absolute prerequisite for the birth of a new one.
Out with the old, right?
Basically, the lambda CDM model has been comfortable, but it clearly is not the whole truth. This cosmic wall is dragging the scientific community out of its comfort zone, forcing a ground-up rewrite of how gravity, space, and time interact on the largest possible scales.
Let's summarize the ground we have covered today, because it's been quite a journey.
It really has.
We started by examining the GWST data, revealing a massive wall of galaxies in the ancient cosmos, a structure whose very existence breaks the timeline of gravitational formation.
Right. And from there, we critically examined the multiverse bruise theory. We explored the mechanics of how a collision between our universe and a foreign bubble could create a hyper-dense shockwave, seeding this wall long before standard physics would ever allow.
And finally, we unpacked the fallout for modern physics. We detailed how a localized, massive structure shatters the assumption of a uniform universe, effectively breaking the equations we use to understand the expansion of space-time itself.
The implications of this deep dive go far beyond the pages of an astrophysics journal.
They really do.
They change how you orient yourself in existence.
That's a great way to put it.
The next time you step outside and look up at the night sky, consider the vastness you're staring into. You aren't just looking out into an endless uniform void.
Not anymore.
No. Somewhere out there, hidden in the deepest redshifts of the cosmos, you might be looking toward a literal boundary line, a physical scar from another reality pressing against our own.
And I want to leave you with one final mind-bending thought to mull over tonight, building on that collision idea.
Go for it.
If a foreign universe really did collide with ours billions of years ago to leave this permanent cosmic bruise, is it possible the boundary isn't perfectly sealed?
Oh, wow. Like a fracture.
Exactly. If this wall represents a fracture in our bubble, could the alien laws of physics from that foreign universe be slowly leaking through the scar into ours?
That is a terrifying thought.
Right. And if they are, how might they be subtly altering the very fabric of our reality in ways our instruments haven't even begun to notice?